welcome to the AI seminar, I guess. I'm Justin Johnson. I'm a new assistant professor here that just started this semester. And today I'm going to tell you about some of my research, both past and slightly more recent as well. So the title of this talk is From Recognition to Reasoning. And the way that I like to start this off is that I work in computer vision. And computer vision is very broadly about building computer systems that can process various types of visual data. And one very important task in computer vision is the task of recognition. And recognition is basically the very broad category of computer vision tasks where you want to have systems tell you what they see in images. And this actually used to be, this is a really big part of computer vision. It's very important. It has a lot of important applications. And it actually works really, really well now. So here are some example predictions from a fairly state-of-the-art recognition system called a Panoptic Feature Pyramid Network. But basically what it's doing is it can input the pixels of an image and then tell you, and then give a category label to every single pixel in the image. So it knows that the blue pixels, for example, in the upper left-hand image are some kind of car. It knows the red ones are people. It knows the green ones are grass. And not only that, in addition to labeling pixels, it can also separate the instances. So it knows what the identities of the people, which people belong to which pixels belong to each person. And you can see that these examples work like really, really well, assuming you have a lot of data. But basically this recognition task I think works really, really well. But my perspective is that there's a lot more to computer vision than just recognition. I think that computer vision should be about not just telling what we see in images, but also building systems that can think and reason more deeply about the visual stimuli that they perceive. So the overall goal of the kind of high-level goal of my research is generally to push towards systems that are more generally visually intelligent, that sort of combine both understanding what they see in images, and also doing something else with that information. And I like to think of this as not just recognition, but some component of reasoning, because it requires us to both tell us what we see in images, and then do something else with that information. So today, to give you kind of a flavor of the types of problems that I think about, I want to talk about 3 different application domains of things that I've worked on that kind of move forward from this basic recognition system to systems that can do some kind of reasoning with the things that they perceive. So then we'll talk about some tasks in linguistic reasoning, some tasks in physical reasoning, and then finally some tasks in 3D reasoning. So linguistic reasoning is actually stuff that I worked on in my PhD for many years. So this is a little bit older work, but I wanted to talk about it just very briefly to give you a sense of some of these problems that I care about. So with linguistic reasoning, we want to combine somehow visual understanding of images with some additional linguistic understanding as well. And there's many different ways that we can instantiate that. One is building systems that can not only tell us the category labels of objects that they see in images, but actually generate full language descriptions of visual content that they see in images. So we can instantiate this as an image captioning task, where systems are presented with an image and they're supposed to generate like sentence descriptions of stuff that they see. So one project that I worked on here is this notion of dense captioning, which is where systems are supposed to input a single image, detect all the objects in the image, and then output grounded language that are attached to each of these interesting regions that the system detects in the images. So for example, our dense captioning system can look at this image and then pull out a bunch of interesting regions, and for each region, talk about it in natural language. So it can give us descriptions like a horse pulling a cart, a wheel on a cart, a window on a building, a horse in a picture, a large white umbrella, a woman sitting on a bench, man sitting on a motorcycle. That one's actually wrong, but if you kind of look at if you zoom in on just the yellow box, it kind of looks like he's on a motorcycle, or a cart with a cart. So you can see that this kind of visual description is moving a little bit beyond basic recognition, because now a system needs to not just say what it sees with the category labels, but actually generate cohesive language outputs. But this is still basically pretty much a recognition task. The system is just telling us what it sees in the image. So another type of linguistic reasoning that we can think about is question answering. So here, we need to move beyond just having systems tell us what they see in images. So here, a system is supposed to be presented with an image and some natural language question that it needs to answer that pertains to the content of the image. So for example, we might be given an image and the question that says, how many spheres are left of the big sphere and the same color as the small rubber cylinder? So you can imagine that in order to solve a question like this, we need to both perceive what we see in the image, we need to recognize all the objects and understand their visual properties, but we also need to understand the language that we're being presented with. And then we need to somehow combine what we've seen in the image with our linguistic understanding of what the question is asking us, and then arrive at a final answer. So I built a big data set a couple of years ago that really tried to stress test this aspect of visual reasoning with these complex natural language questions called the CLEVER data set. And you can see that these questions are like pretty non-trivial. You need to in order to answer this question, you would need to recognize the objects, you need to count the objects that have different types of properties, you need to understand spatial relationships like things left of things and right of things, and you need to be able to compare objects to see which objects have the same material properties as other objects. So to tackle, one, we built this big data set to kind of stress test visual reasoning. And then another thing that we can try to do is build new models that can now perform this type of compositional reasoning to answer these sort of complicated, complex questions. So we built this big neural network system that has sort of two major components that kind of factors out these different components of visual reasoning. So the first component is this program generator that's going to input the raw text of the question and then output some set of primitive operations that need to be performed or need to be answered in order to actually operationalize the question and arrive at an answer. So in this case, if we get this question of, are there more cubes than yellow things, then what we need to do is first find the cubes, count the cubes, then find the yellow things, count the yellow things, and then finally compare those two counts. So this program generator is supposed to convert from this raw natural language input to this structured program that gives us a set of steps that the system should take in order to arrive at an answer. And then the second component is going to input the image and the predicted program, and then actually execute the program in some way to arrive at an answer. So it should actually count the cubes and count the spheres and then compare them and get an answer. And because we live in the age of deep learning, then both of these components are implemented as giant neural networks. So the program generator, yeah.
So does the program generator see the image? Is that ever relevant to know what the right program should be to?
So in this setting, the program generator does not see the image. But that's kind of by design in the data set. We know that the language alone doesn't contain any ambiguities. But there's sort of other versions where you might thread that image information through the program generator, and especially in situations where there might be visual ambiguities, then you would probably need that information. But we didn't need, but by construction, the data set doesn't have those ambiguities. So then the first component for the program generator is a big recurrent network, sequence-to-sequence model, that inputs the words one at a time and then outputs the program tokens one at a time. And now this you can kind of train up using a standard sequence-to-sequence approach. Now the execution engine is a bit more interesting. So here it relies on this formalism called a neural module network that was proposed by Andreas et al. Back in CPR 16. And the idea here is that the execution engine now contains a little inventory of little neural network modules, where there's one module for each basic primitive token in the programming language. Each of these little neural network modules is itself just a little tiny neural network block. But now the idea is that we're going to compose these modules in a way that mirrors the structure of the predicted program. To give, for each predicted program, it gives rise to this custom neural network architecture, which is specialized to answering that particular program. And for each program that we generate, we're going to arrange the modules in a different order to generate this custom neural network. And then this thing can be trained up and then given an answer. Now, a big shortcoming of this approach is that we actually have to supervise it with paired questions and programs. But there's sort of follow-up work, including from Karen, that gets away with less program supervision with these type of models. So that's kind of one task of linguistic reasoning, is answering questions. A third type of linguistic reasoning that I've worked on is actually going the other way around and starting from a bit of language and then using that to actually generate custom images that match the language. So for example, you could input some complex sentence, like a sheep by another sheep standing on the grass with sky above and a boat in the ocean by a tree behind the sheep. And what we want to do is generate some kind of image that matches all the interesting relationships and semantics of that sentence. So people have worked on this before, but they really only got it to work on relatively short, simple sentences. So when we applied kind of state-of-the-art natural language to image generation on this task, we saw that it doesn't really generate these kind of scrambled images that didn't work so well. So our approach was actually to change the input representation. So rather than working on the raw natural language, we work on this scene graph representation of a language instead, which makes explicit all of the objects in where now this scene graph representation has a pink node for each object and a blue relationship node for each binary relationship that exists between the two objects. So now this scene graph at the bottom kind of conveys the exact same semantic meaning as this natural language little sentence on the top, but it's sort of parsed out into this structured graph representation. And then we built a model that can input these kind of structured scene graphs, and then from that generate images that match the semantic content of the scene graph. So in this example, we're actually able to generate these fairly nice images that actually do correspond, that actually do respect all of these complex relationships that can occur in these input images. And there's been some prior work from some other people on converting languages to scene graphs, so we just focused on the scene graph to image component in this project. Now, but really cool thing about this scene graph to image representation is that it lets us sort of edit the image and start from a simple scene graph and then make it progressively more complicated as a way to do sort of like semantic image editing. So for example, we can start with this simple scene graph where we want to have a sky above the grass and a zebra standing by the grass. And here we're writing it out in natural language, but these would actually be presented in graph form to the model. And then we can see this, the system generates what seems like a zebra standing on the grass. Now we can change the zebra to a sheep, and we can see that both the appearance of the animal changes, but also the appearance of the grass changes too, because probably sheep and zebra tend to live on grass of different colors. We can add a second sheep to the scene. We can add a tree behind the sheep. We can add an ocean by the tree. We can put a boat in the ocean. And then even more, and this was the really exciting one, we could actually move that boat onto the grass. So here, the data set probably didn't have very many examples of boats on grass, but because we work on this sort of factored scene graph representation, I think we're able to better disentangle these different relationships and actually generalize these more complicated situations. So this was a lot of my prior work on ways that we can use language to build computer vision systems that dive deeper into images. Yeah, was there some question?
I had a question. So in all of those examples, you provided sky above grass initially. Did you find like training on data you didn't catch that prior sort of automatically, such that if you provided the second part of the sentence, would it have the sky at a different location, or sort of not follow this common sense?
Yeah. So the problem is that all the examples that it saw during training were graphs that always talked about the sky. So if you give it a graph at test time that doesn't include any relationships about the sky, it's basically an out-of-sample input for the model. So it tends to generate garbage when you get out-of-sample inputs. But I think figuring out ways to make that more robust would be an interesting follow-up idea.
I see that mainly you try to represent nouns. Would that work with adjectives as well? So let's say bluegrass or something like that.
Yeah, I would really like that to work, but the problem is it's very difficult to get that kind of data. So we worked on this data set called Visual Genome that we built at Stanford, which actually does have attribute data, so I actually tried for a long time to get attributes to work in this model as well, but it turned out that the attribute annotations that we had in the Visual Genome data set are fairly noisy and didn't give enough signal for training. So I think like model-wise, incorporating attributes is fairly straightforward. The question is where are you going to get a source of this kind of relationships and attributes in a clean way. So that I think was the main bottleneck. Thanks. So that's basically a lot of my past work on linguistic reasoning. So that's all kind of stuff from my PhD from a couple years ago. So then these last two tasks are things that I've been working on more recently. Yeah, was there a question before we move on?
Yeah, one more question related to the attributes. Do you think you could learn the attributes sort of like as a separate channel to the objects, or would you have to learn, the meaning of blue for like all the different object categories separately? Like learn what is a blue sheep versus blue grass?
Yeah. Well, so sort of in the model already, we're kind of factoring out the relationships in the objects. Mm-hmm. So like we learn like the concept of left of, and then left of sheep and left of boat are kind of the same thing. So you could, I think the model, like I said, the model could, I think, work for attributes as well, and also factor out like blue sheep versus blue boat. But I think we're really lacking high quality training data, so I don't actually know how well it would work. Mm-hmm. But at least conceptually, you can hook up the model in a way that would allow it to do that kind of generalization.
in visual genome, aren't there a bunch of relationships like automatically annotated as next to and above and then below and stuff?
So in visual genome, there are not. They're all manually annotated in visual genome. We also train this on Coco, and on Coco we use the geometric layout of the objects to generate the relationships automatically.
The open, what about open image? Is that it? I don't know, anyway. But what I was going to say is that some of these attributes could be grabbed automatically, like, you know, you can maybe figure out if something's blue or not.
But I don't like that, because sort of philosophically, if you can detect the attribute automatically, then like, what are you learning? And if you could detect it automatically already from the raw pixels, then you probably didn't need it as explicit input to the model anyway. All right, so then maybe the next, another sort of thing that I've worked on more recently is this task of physical reasoning. So here, we want to build systems that not only sort of perceive what they see in the world, but can actually learn to manipulate objects and interact with the world in some way. And this is something that animals can do, right? So for example, we can get these adorable sea otters that actually know how to like take clams and smash them with rocks and use that to open up the clams and get the food inside. So this idea of is that animals can do not only can they see what exists in the world around them, they can actually manipulate objects in the world around them to achieve goals, like getting the tasty food outside of the clam. And we can actually, you know, people build robotic systems that can interact in the real world as well. But the question is, can we do this in a more sort of end-to-end learning-based approach? So to kind of tackle this problem, we actually took inspiration from some folks who have tried to study the intelligence of different animal species. And one way that people have tried to study the intelligence of animal species is actually building these little puzzles that animals need to solve. So it turns out that actually crows are like really, really smart. And crows can be taught to solve these puzzles where there's a piece of food inside of this plastic tube, and the crow has a stick, and he needs to somehow use the stick to get the food out of the plastic tube. And crows are really smart, and they can actually learn to solve these sort of physical reasoning puzzles to sort of manipulate their environment to pull out the food from this tube. But what's really amazing about animal intelligence is that animals can not only learn to solve these complicated physical reasoning tasks, but they can also generalize their physical reasoning knowledge to quickly solve new types of related tasks. So what I thought was really fascinating about these crow experiments is that you can set up sort of multiple conditions of this physical reasoning task. So maybe in one condition, there's kind of one configuration of this trap that's kind of like the training phase for the crow, and the crow maybe takes a while to learn to solve this puzzle, but he'll eventually get it. But then after this crow has learned to solve this initial version of the task, we can present him with a different version of the task, where somehow the exact low-level physics of the situation, or the exact physical manipulation that needs to be done to solve the task, is now different. So what's particularly cool about animal intelligence is that not just that we can solve complicated physical reasoning tasks, but that once we know how to solve a physical reasoning task, we can generalize our knowledge to be able to quickly solve related tasks that involve related types of physical reasoning. So what we wanted to do is try to operationalize this idea of generalizable physical reasoning into some kind of concrete computer vision benchmark. So with some collaborators at Facebook, we built this benchmark called PHYRE, which is a new benchmark for physical reasoning. And PHYRE was sort of inspired by these kind of animal manipulation tasks. So what does it look like? So in the PHYRE benchmark, the agent is presented with this initial scene, which is this like complex configuration of objects in space, and they're given some goal that they need to achieve in the scene. Like add one ball to this scene such that when physics plays out, then make sure the green ball is touching the blue ball. So then you can imagine humans trying to solve this task. You can go in there and put a ball into the scene and adjust the size and position, play out physics, and it looks like we missed. So then we can kind of try it again and use our knowledge of what happened in the previous trial to adjust the size, adjust the position, play out physics, and then now it just barely goes in there. So this is the PHYRE task. So kind of the design goals of PHYRE, one, we really want to focus on physical reasoning, and especially we want to focus on generalizable physical reasoning. So we care not just about getting systems that can solve these tasks, but we really care about systems that can generalize their physical understanding to solve related tasks with very few trials. So we care about sample-efficient generalization in this PHYRE benchmark. So what is PHYRE a little bit more concretely? One, we have these set of environments where each environment is a scene and a goal, and then based on that initial environment, agents make some action, which is putting new objects into the scene. Then given that action, you play out the simulation and see whether or not the goal was solved. So given this large set of environments, we provide this large set of environments as well as a set of evaluation metrics. So the environments are all kind of built on this 2D physics engine called Box2D, and all of the environments use the same physics engine and the same types of objects, but their exact configurations and the exact goals and the exact way that objects need to interact might vary from environment to environment, but the underlying physics is all the same. And we really care about generalization. So we provide a fairly large set of different physical environments for systems to play in. So to study generalization, actually each puzzle doesn't exist in isolation. Each puzzle we view as an instance of a puzzle template. And these puzzle templates are sort of like slight variations on the same puzzle where the objects might appear in slightly different positions or locations. So in this visualization on the right, each row is now different samples from puzzles that share the same template. So for example, in this middle row, what you need to do is kind of knock over this big stick and then cause the green ball to kind of fall onto the floor. But you can see that in different instances of those puzzles, the exact height of the stick and the radius of the ball and the X position of the stick are all varied. But kind of the underlying physics of like you need to knock the thing over and get it on the floor is the same in all of these. So within PHYRE, we have sort of these two levels of generalization. One type of generalization is generalizing to novel instances of the same template. So here what we want to do is, during the training phase, the system has access to maybe some subset of the task instances for a set of different templates. And now at test time, it needs to generalize to novel instances of those known templates. And then, of course, there's a more complicated form of generalization where systems need to generalize to a novel set of templates at test time. So they need to train on some set of templates, and then at test time they're presented with novel templates that have sort of very different physical interactions. And within PHYRE, we also provide two different tiers of complexity. So the first is tasks on the left that can be solved by adding just one new object into the scene, whereas tasks on the right actually require us to put two new objects into the scene in order to solve the task. So once you put two objects into the scene, that's sort of like a lot more complicated to imagine all these physical interactions, and now the action space of all the different possible actions is much, much larger in the right-hand side. So then the evaluation metric that we care about is that, like I said, we don't actually care about just getting systems to solve these tasks, because in fact all of these tasks are solvable using brute force search, and this was by design. So because it's actually kind of tricky to set these puzzles up in a way that you know that they're solvable. So by design we made sure that all of the puzzles in the PHYRE benchmark, if you like burn a lot of compute, you can just brute force a solution to all of them. But the real measure of success is efficient generalization. That we want to build systems that during training time, sure, do whatever you want to do, burn a lot of compute, but now at test time, you should be able to have only a few trials on the novel tasks and perform well. So then sort of during the setup is that during training time, you can spend as much compute as you want, and now at test time, you're only allowed 100 attempts at each novel task, and your goal is to solve each novel task as quickly as you can. So then our evaluation metric, to make this quantitative, we draw this success curve, where on the x-axis we draw the number of attempts at the novel tasks, and then the y-axis is the fraction of novel tasks that were solved after you do that many attempts. And then we always draw the x-axis on a log scale to kind of emphasize solving tasks very quickly. And then the metric is computing the area under this curve. So here, this AUCCESS metric, area under the success curve, for this brute force search on the two-ball task is only 2%. So this works really poorly. So even though brute force search will eventually solve them all, We care about efficient generalization, and random search does not efficiently generalize very well. So on the other hand, in order to get AUCCESS of 100, the only way that you can do that is if you solve all of the novel tasks in a single attempt. So that's quite a hard metric to get 100% on. And then maybe 50% would be solving half of the tasks in a single attempt, or maybe solving all of the tasks within 10 attempts due to the log scale. So this AUCCESS metric really we want to trade off both the fraction of tasks that are successfully solved, as well as the system's ability to quickly generalize and solve those tasks in very few attempts. And so basically our initial experiments on this PHYRE benchmark are really kind of setting up the benchmark. So far we've tested some really simple baseline models, but we haven't tried anything too complicated yet. So there's sort of two different approaches you could imagine to solving this task. Oh yeah, question?
What are the physics rules of incorporating the data set?
Yeah, so it's pretty simple Newtonian physics. So there's kind of gravity and collision and friction, and that's about it. And gravity is just everything is pointed down. There's no different balls attracting each other due to gravity. And then it's hard to write a physics engine, so we kind of just we build on top of an existing open source physics engine called Box2D. But yeah, all the physical constants are the same between simulations. The force of gravity is always the same, the masses and densities of these objects are always the same.
And do you think it's easy to scale that up when the physics become more complicated?
Maybe, I'm not sure. I think we've yet to solve this task even in this unscaled regime. So then maybe don't worry about scaling until we can get it to solve the simple problem first. But I think actually the biggest bottleneck in this was just inventing new tasks. So it took a lot of human effort to design all of these puzzles, which was kind of fun, but also took a lot of human effort. So there's at least kind of two paradigms that you can imagine for solving these tasks. One would be something that the kind of most intuitive is that it inputs the description of the task and then just directly outputs the action that you want to take, the position and radius of the ball that you want to add to the scene. But we actually for our simple baseline experiments, we actually tried approaches based on ranking instead. So what we're going to do is we're going to generate some large sample pool of candidate actions. And then we're going to build systems that re-rank those candidate actions with the hope that actions that are going to solve the task are going to be ranked up the beginning. So and then for fair comparison, all models are going to always rank the same set of candidate actions. So we try sort of different approaches. One is sort of random order, which is basically a brute force search. Another is a type of memorization, that we're just going to remember which actions had the best performance on the training set tasks, and now repeat those actions at test time. So then if there was one particular action that worked really well on the training set, we'll just directly memorize that on the test set.
Are those actions they're specific to the scene?
Yes, so they're random actions, but they're enough random actions that there is a solution in there somewhere.
But what does it mean to remember what you did in the training set if the test will be on a different instance of the template or a new template? What's the interaction?
Yeah, so in that case, it has to be the same set of actions of both the training and the test time, yeah. Yeah, so then it's the same set of 100K actions at train and test, because they're just 100K random actions that are kind of sprinkling over the entire scene.
Right, but so the same action in the train set and the test set would still be put the ball
in the exact same place.
Okay.
Yeah, right, so this is not really this is not a good metric. This is not supposed to be a good method,
yeah.
Right? This is a method to see if there's bugs in the data set. Because if this method does well, then we've done a bad job of building a data set. So that's not supposed to be a good method.
Mm-hmm.
And then our slightly fancier method was a kind of DQN, where basically it inputs both the initial scene and the initial action, and then gives a score that is the probability that the task will be solved, assuming that we take this action in this scene. And this can be seen as a type of deep Q network. So then we have some results. Here is that they don't work that well. So on the right-hand side, we see this plots of generalization to novel template to within template generalization. And here we see that DQN actually does a fairly reasonable job, but the other baselines do pretty poorly. But on this cross template, you see that it actually doesn't work that well. we also consider a couple online versions of these algorithms, right? Because they're allowed 100 attempts at test time, so we should also be able to build models that kind of update their information over the course of those 100 attempts. So for two really simple approaches to that, you could have sort of an online memorization, which now is going to update the statistics about which set of actions worked well, and update those statistics as it makes its 100 attempts on the test set. So then maybe if you're presented with a novel template, that maybe if there's one action that works really well with the entire test set, then this online memorization should work well. And then an online DQN is actually making gradient steps during the 100 attempts that we make while streaming over the test set. And these do a little bit better, but actually not that much better than the fully offline approaches. So I think there's a lot of space to improve on this task. So basically, where we are in this project is that we've kind of proposed the benchmark, and we've got this initial set of tasks, these initial set of models that are not very smart, but that basically convince us that the benchmark is not broken. And that's kind of where we are right now. So I think the next step in this physical reasoning direction is now to build smarter agents that can actually do some more intelligent reasoning during both training and evaluation in order to solve these types of puzzles. So I think that's definitely a next direction that I'm excited to work on in the future. So and then of course this is all online. We've got a fancy URL, PHYRE.ai, and there's actually an online web demo, so you can actually go and try to play with these tasks yourself online. So any questions on this physical reasoning stuff? Yeah.
How do humans do physical reasoning? It is simulation. Like, do you imagine and then you execute, or is it you just execute and then you like? Is it trial and error for you, or is it like you first imagine this might work and then you execute it and then you see it?
Yeah. So I mean, well, we didn't study that in this paper yet. Actually, there was kind of a cool coincidence that we built this PHYRE benchmark, and we were focusing on like agent performance. And at the same time, there was a group at MIT from Josh Tenenbaum's group that built quite a similar benchmark, but they were focusing on evaluating human physical reasoning. So they built actually a benchmark that looks very similar to ours, but their whole paper is about like seeing how humans perform and generalize on this task. So we're planning to hopefully collaborate with them and kind of bring the human understanding that they did into our benchmark and take the agent understanding that we built and put it into their benchmark. So I think that's something I'd like to explore more in the future.
Two balls is cool, but if I'm thinking about this task, I think about like my inability to plot a couple of ricochets, like as if it's a billiards table. Have you thought about another difficulty too that's about like how many bounces or things? Yeah. Okay.
Yeah, we thought about it, and we had endless arguments about it, and we could never come to a good consensus on a good concrete way to measure that. But yeah, I think that would be quantifying that complexity in that way. I think is a really good idea.
What's the like temporal aspect of when you run the DQ in there? Like, does the agent actually see the simulations play out?
No, so that's actually a big shortcoming in all these methods right now. That right now it's just like right now we actually get this whole intermediate simulation, but that information is not being used by the agent by any of these methods right now. So clearly we need to have some follow-up work that does use that new information, and I think that's like where we need to go with this.
Is there any prior on the physics, like the defined physics of the simulator? Like say for humans, if they would like to do this, they might assume that the gravity is pointing down, right?
Oh,
so
I
like
see.
This particular example where they put the two balls, humans might make an assumption that the stick will fall down and then it will bounce, right? But the models won't. So is there any prior information fed while like enumerating the actions for the DQN or such?
There's not, because the sort of underlying physics is always the same. But I think you could imagine using the same paradigm to kind of probe that question. And then see like if the physics has gravity going down, how quickly do humans solve the task? Versus if gravity is like going upward diagonally or in some curved path, then maybe humans will take longer to solve it. So we didn't do that at all, but I think you could do that with this paradigm.
I realize this is a follow-up to the last question. I realize you haven't done like the official like IRB type experiments or whatever, but do you have any sense of how well you do compared to these machines? Because I'm very curious what the answer is, essentially.
These tasks are actually really hard.
Yeah, they strike me as, I mean, the sort of classic joke that when Josh was showing off is like, when you're stacking things, you're like, well, I mean, sure, if you're a barista or you're a busboy, you stack plates, but like, how often do people actually stack up blocks? My question sort of is how I would have, I mean, Angry Birds is a wonderful way of wasting time, and I'm very curious whether you could actually get superhuman performance on these types of tasks, because humans are just bad at these tasks.
I think you actually could get superhuman performance on these tasks. I mean, part of it is like our UI kind of sucks right now for playing with this thing. So I think with a better UI, it would be easier to solve it more quickly. But like, what you need to do is a lot of fine-tuning of the exact positions of the balls to get it to solve the task. So you saw this example where like it falls down and the ball flies over and goes in the cup. For that to work out, it needs to be like pretty damn perfect. So those type of situations are actually pretty tough for humans.
Yeah, I can imagine you could do lots of very cool things if you can get superhuman performance.
Exactly, because then you could imagine really cool models that like look at set up the qualitative path that it actually followed and the path that you wanted it to follow, and then kind of like refine and do some gradient descent or binary search or something on the exact position of the object. So I think there's a potential for really cool models that make use of that.
So one more cool work which is very related to this is basically the one of throwing things inside a bin. It's a robotics paper where they basically compute a physics-based path and then make the engine learn the extra noise that actually needs to be fine-tuned, which is brute force to take a lot of time to really search the fine solution in there. That could probably be something that could be tried with this.
Yeah, I think so.
Because I think getting the initial solution is easy. Getting the exact solution is hard.
Exactly.
So while you have the pixel space, if you detected the locations of every image and then encoded it as such, like for every ball, its radius, its X and Y location, do you think it would be easier or more difficult to learn? Because at one side you're reducing the space, but at the same time, sort of a lot of the relationships you get for free for an image, but might be harder to sort of deduce from the symbol.
I mean, I think that might be easier, but it also kind of like, one way to solve this problem is just like have a simulator and do brute force attack on the simulator. So to me, I think the interesting part is not models that have an existing simulator baked in, but somehow models that can learn the rules of physics implicitly and then use those learned rules of physics to solve the task. Because we don't actually care about solving this, but we maybe do care about systems that can understand rules in complicated situations and then plan according to those rules. So I think whenever you build synthetic benchmarks like this, you've got to be really careful, I think, in realizing that the point is not to get a high score on the benchmark. The point is to build systems which you think have the capacity to generalize, to like have the same method work in real world stuff. But that's always a big challenge when you're thinking about the types of models to deploy on these types of synthetic benchmarks.
But just to follow up, I guess my question is like when I look at this, I think okay, like there's a ball there, there's a line there, it's gonna fall. So like automatically it's factoring out a lot of those things from just like this grid of pixels.
Yeah.
And I'm just wondering if by going to that step first, would that be a good step, or should we just consider it from images to stuff without any intermediate?
I don't know. That's why it's research. But I think that having an object-centric versus image-centric, I can see pros and cons to both approaches, and I think that's why we need more follow-up work on this type of task.
But that's how you do it now. You learn the physics roots implicitly, right?
Yeah, but it's all image-based reasoning. It never it never explicitly represents objects and their relationships. It's all kind of image pixels. So then, for sake of time, I think we should move on to the third branch, which is 3D reasoning. So the world is 3D, but computer vision is usually 2D. So recognition is usually recognizing 2D stuff in images, but I think we should recognize 3D stuff in images too. So we built this system called Mesh RCNN last year that actually generates 3D. We can predict 3D shapes from input 2D images. So why study 3D perception? One is that I think there's a lot of practical applications for a lot of real-world use cases. One is something like autonomous vehicles. They need to navigate in the 3D world and not hit other objects in the 3D world, so we should be able to build recognition systems that know about 3D. Another is maybe future applications in AR, VR. That if humans are now going to natively consume computer-generated 3D content that's going to be overlaid in the real world, then we should be able to process that type of data with neural networks. Then I think there's also the high-minded sort of AI goal, which is that the world itself is 3D. And if we had computer vision systems that had knowledge of 3D inside of them, then we might be able to do better at even classical 2D recognition tasks. So I think maybe we could better recognize these cluttered puppies if we understood the 3D structure of them. Or we could recognize these maybe objects from novel viewpoints, like the cat on the bottom, if we understand the 3D structure of cats and how cats usually look like. So one more project in this direction was this Mesh RCNN project that I did with some folks at Facebook. And here the idea is that we want to input a single RGB image, and then the output we want to detect all the objects in the image, and for each detected object we want to emit a full 3D triangle mesh, giving the 3D shape of each detected object. So now all the object detection stuff, we kind of build on all of the latest and greatest state-of-the-art in 2D detection, which is Mask RCNN. And all the interesting stuff is this 3D triangle mesh prediction step. So we somehow need to predict 3D triangle meshes using neural networks. So the basic paradigm that we use for outputting a mesh from a neural network is this idea of iterative mesh refinement, which I became aware of this paper from Wang et al. At AUCCESS 18. So here the idea is that you're going to start with some initial guess for the 3D shape of the object. And now the neural network is going to process that initial shape, process the input image, and now regress vertex offsets for each vertex to move each vertex from the initial mesh. And then you can repeat this many times, and at each time step you're going to update the vertex positions of every vertex in the mesh. And over time it should generate a nicely well-structured mesh that matches the input geometry of the object. A big problem here, of course, is that you're constrained in the topology of objects that you can model. You're constrained to only model objects that have the same topology as that input mesh. So for example, if you're always deforming from a sphere, then you can never predict a donut, because there's no way that you can continuously deform a sphere into a donut. So our solution to overcome this problem in Mesh RCNN was to use a hybrid shape representation. So by that, I mean first, the pipeline kind of looks like this. So first, we're going to input a single RGB image. Then we're going to do all of our favorite 2D recognition stuff. So use sort of Mask RCNN machinery to generate 2D bounding boxes and labels and semantic segmentation masks for all of the objects. Then from there, we'll also predict a very coarse 3D voxel representation of each object in the scene. And then these coarse 3D voxel representations will then be converted to meshes and refined using this idea of iterative refinement to then generate these very precise 3D output meshes that match the exact geometry of all the objects. So then to kind of step into the architecture in a little bit more detail, basically we run Mask RCNN, which is the state-of-the-art 2D object detection system. And then for every box that Mask RCNN outputs, then we attach this mesh prediction head on each box that Mask RCNN is looking at. So all of this stuff for predicting the boxes, predicting the masks, predicting the object categories is all the same as existing 2D stuff. And now first, we have this voxel branch that's going to predict these coarse voxel occupancy grids for the objects. And we do that using these voxel grids which are aligned to the camera space, which means our voxel grids are actually these little frustrums-based regions instead of cubes. But actually doing this camera aligned prediction, I think, allows things to generalize much better. And then the next step is to take your predicted voxels, threshold the probability at some threshold value, and convert that, and that gives you some binary voxel occupancy grid. And from there, you can convert the binary voxel occupancy grid into some initial mesh. And that initial mesh is just like a boxy version that goes around the outside of all of the active voxels. And that gives us this initial QB mesh. Then once we have that QB mesh, then we can go into this idea of iterative mesh refinement that's used in prior work on mesh prediction with neural networks. So then within each refinement stage, we actually we interleave three different operations. The first is a vertex alignment operation that allows us to get image features for each vertex in the predicted mesh. So what I mean by this is that we take our current predicted triangle mesh, we project the positions of the vertices of that mesh onto the image plane, and that gives us a 2D position in the image plane for each vertex in the mesh. And now for each of those projected vertex positions, we can sample an image feature from the backbone CNN using bilinear interpolation, which is a similar procedure that's done for cropping boxes differentiably inside Mask RCNN. But what this does is basically gets us an image-aligned feature vector for every vertex in the mesh that tells the system kind of what is the local appearance of the image in the neighborhood where this mesh or this vertex would appear in the input image. And this is kind of a natural way that allows us to fuse the visual information coming in the input image into the geometric mesh that we have. Then the next stage that we use to propagate that information along the mesh is a graph convolution layer. So then in graph convolution, it's an extension of normal 2D image convolution to work on arbitrary graph structure data. So the idea is that the input is a graph with a feature vector attached to every vertex of the graph. And at the output, we want to predict a new feature vector for every vertex in the graph using some operation that sort of spreads information along the edges of the graph. So here the graph is just the edges that exist in our triangle mesh. The initial features are kind of the 3D positions in space of each vertex, as well as these visual feature vectors. And then graph information kind of fuses this information along graph edges. Then we have this mesh refinement where it predicts some updated position for every vertex in the mesh. And that is just going to not change the mesh topology, just adjust the geometry a little bit. So then we have multiple stages of mesh refinement that eventually are going to output this final triangle mesh. So we actually have a lot of training losses for this thing. We've got all the ones from 2D, from mask RCNN, we've got to juggle 5 losses, RPM classification, all these existing losses from 2D detection. Then we're adding on these additional 2 losses for 3D shape prediction. One is this voxel loss, and one is this mesh prediction loss. And it's kind of interesting to think about, like, what does this mesh prediction loss even look like? This is kind of an interesting technical question. So the idea is that we predicted a mesh, and we have a ground truth mesh, and now we need some differentiable way to compare meshes. And we want and in particular, a challenge is that you can represent the same 3D shape using different triangle mesh representations. And we like our loss function to be invariant to the particular way that we represent the shape. So for example, you can represent a square using 2 triangles or 4 triangles, but it's the same shape. And our loss function shouldn't care about how exactly we represented this in triangles. So our solution is to use a third 3D representation, which is a point cloud representation. So what we're going to do is, for the loss, we're going to convert these 2 things into point clouds and then compare them as point clouds. So we're going to sample a bunch of points on the interior of the ground truth, sample a bunch of points on the interior of the prediction, and then compare those 2 sets of samples as point clouds. And this allows us to no longer care about the exact triangle parameterization.
What is the comparison metric from points to points? Is it point to point or?
I'm glad you asked, because that's right here, right? Jump the gun. But there's a couple technical problems here. One is that sampling the prediction needs to happen online, so that needs to be super efficient, and you need to be able to differentiate through that sampling operation. But it turns out there's ways that you can get around those problems. Then the other question is, how do you actually compare point clouds? We've kind of just like kicked the can down the road. So there's a point-to-point distance called a chamfer distance that people use to compare point clouds. The idea is that given maybe 2 sets of point clouds, the orange and the blue, we use a sort of bidirectional nearest neighbor matching. So then one term is that for every blue point, we find its nearest neighbor orange point and take the sum of Euclidean distances for every blue point to its nearest neighbor. And then similarly, for every blue point, for every orange point, we find its nearest neighbor blue point and take a sum over those Euclidean distances. So that lets us now actually train these mesh predictions, these mesh predictors. Turns out there's a problem though, is that those 7 losses weren't enough. And if you train only with those 7 losses, you get these very ugly degenerate mesh predictions. So then if you train only with this sort of point matching loss function, then you get mesh predictions like the middle column, which sort of match the ground truth shape, but are these kind of ugly degenerate meshes with all the triangle faces folded over on each other. So we can get around that by adding some additional sort of shape regularization term into the loss that sort of prevents the model from predicting ugly meshes. And the particular shape regularizer that we found to work quite well is just to penalize the Euclidean distance of all the edges in the predicted mesh. And just by adding this additional shape regularizer, then you get these very beautiful meshes on the right that both match the input shape and have kind of a nice, well-defined triangle mesh structure. So we compared some baselines, and our bars are bigger. But I think that what's really interesting is to look at the qualitative comparisons. So one of our major baselines is some method that just deforms from a fixed sphere and does not go through this intermediate voxel prediction. And there you can see that this middle row that deforms from a sphere just can't properly capture holes in objects. So even though for like the chair on the left, the middle model kind of knows that there shouldn't be any vertices there, so it pushes all the vertices away from the hole, but it just can't properly model the hole because it's deforming a sphere. Whereas our model on the bottom can properly output objects with these complicated topologies. We also show some results, but on this Pix3D dataset, where it's more real world, and we need to jointly detect objects and predict these full triangle meshes. So then you can see that we predict these full, not just the visible parts of the meshes, but also the invisible parts, which is pretty exciting. And you see that on this Pix3D data set, because we're kind of built on top of object detection, we can both detect a lot of objects and predict shapes for a lot of objects. We actually do amodal completions, so we predict even the part of the couch which is occluded by the head of the dog, which is kind of an interesting thing because we're working in 3D. Also interesting is that some of the failure modes that we see are actually aligned to failure modes in 2D recognition. So for example, on the left, you see that there's some failure modes around the bookcase, where the 2D recognition part actually fails to properly model some of the pixels in the bookcase. And we see the same failure modes in the 3D mesh, predicted mesh. So that makes me think that maybe even improvements in 2D recognition might also potentially help this 3D shape prediction task as well. Okay, but so that's Mesh RCNN. But there's a big problem with Mesh RCNN. And the biggest problem with Mesh RCNN is that it requires 3D supervision. So the way that Mesh RCNN works is that we've got the input image, the model predicts the predicted 3D, we have some ground truth 3D, we compare the ground truth 3D to the predicted 3D with our loss, then we use that to backpropagate gradients into the model and make our gradient steps. But the problem is that 3D annotations are really expensive to get. So I think that if this is to scale beyond this existing data set of IKEA furniture, then we need to build models that can recognize things in 3D, but that don't rely on 3D supervision. So I think one direction that I'm very excited to work with to relax this 3D, the supervision constraint is this idea of differentiable rendering. So what I mean by here is that we could, an alternative pipeline is that we could have an input image, have the model predict a 3D shape, and now actually use a graphics engine to render that predicted 3D shape back into 2D. And that gives us now a 2D reprojection of our 3D input shape. And then you could have some ground truth 2D supervision, and now define the loss function in 2D between the projected reprojection of your 3D prediction and your 2D annotations in 2D space. Because collecting annotations in 2D is much, much cheaper and more scalable than collecting annotations in 3D. But now the problem with this approach is that you need to backpropagate through the rendering process itself. And that ends up being a fairly complicated piece of code. So with some collaborators at Facebook, one thing that we're releasing soon is a new library called PyTorch 3D, which is meant to unlock a lot of applications for 3D deep learning. And one of the biggest cool pieces of implementation that we have in this PyTorch 3D library is our own high-performance differentiable renderer for this task of weakly supervised 3D reconstruction. So to understand how differentiable rendering works, you need to first think about how rendering works. So normally rendering, you've got a 2D grid of pixels, you've got some set of triangles in the world, and for each pixel, you find its nearest, you shoot rays out from the camera through each pixel, find the closest triangle in Z, and then project that color onto the pixel. But the problem is that this sort of basic triangle rendering pipeline is not differentiable. And actually this has been something that a lot of people have gotten really excited about in computer vision over the past, I'd say, year and a half. So there's been a lot of groups proposing slightly different variants on differentiable renderers. But the basic way that it works is that one problem with traditional rendering is that it's just not differentiable. So for example, if you've got this red triangle and this yellow triangle, and you imagine the color of the pixel as a function of the z coordinates of the triangles, you can see that it's non-differentiable. That as soon as the red triangle goes in front of the yellow triangle, the color of the pixel is going to change all at once. So that's a non-differentiable step function. So the way that we solve this in a differentiable renderer is that we actually we compute the color of each pixel by accumulating the colors of the k nearest neighbors along the z direction. And by blending the colors of the k nearest neighbors in z, then it lets us actually have a more smooth transition as those z coordinates are to change. So then there's another problem with traditional rendering, which is that it's also non-differentiable at boundaries of faces. So now if you imagine the color of the pixel as a function of the x-coordinate of the triangle face, then we're again going to get this step function, where as we vary the x-coordinate, and as soon as the face intersects the pixel, then we're again going to get this non-differentiable step function. So we can solve that problem by kind of blurring out each triangle face. So we extend kind of a blur radius around the exterior of each triangle face, and that actually lets those colors be now differentiable with respect to both the x-coordinates and the z-coordinates. So then you need to write a lot of high-performance CUDA to actually make this work and compute gradients, but That's the basic idea of how the math behind this thing works. So then kind of one application of differentiable rendering is maybe this idea of starting with a template mesh and then deforming it to fit a target 3D shape, but using only 2D supervision. So for example, we can take the target 3D shape and then render it from a bunch of different viewpoints to get these target masks of the target 3D shape, to get these 2D silhouettes of the target shape from different viewpoints. Now what we can do is take our initial shape, render it from the different viewpoints to get the current silhouettes of our shape from different viewpoints, then compare it with those target silhouettes from the different viewpoints, and then back propagate through that rendering process to compute gradients of the silhouette differences with respect to the coordinates of the input mesh. And if you do exactly that, you see that over the course of running gradient descent on the pixel coordinates of the initial mesh, then it sort of allows us to deform that initial mesh to now match the shapes that we wanted to predict. So this is kind of a toy application of a differentiable renderer. But we actually built an even more more interesting sort of project that uses differentiable rendering as a tool to let us do 3D stuff without any 3D supervision. So this was an intern project that I worked on last summer that is sort of currently ongoing. And the idea is that we're tackling this problem of view synthesis. So with view synthesis, what we want to do is we want to input a single RGB image, and then we want to output in RGB images which give novel viewpoints of the same scene. So then at test time, the input is a single RGB image, but then we kind of want to animate the scene using only a single image as input, and now render new views of that scene from different viewpoints. And the way that we do this is using a differentiable renderer. So kind of the pipeline of the model here is that it inputs an RGB image. Then we have two neural networks. One predicts a depth image that predicts the depth of every pixel in the input image. And the other is a feature extractor that predicts a feature for every pixel in the input image. Then you can combine these predicted depths and predicted features to now give a point cloud, a 3D point cloud, where we have a feature vector attached to every point cloud. So then given this predicted point cloud of features, what we can do is now rotate it and render it from a different viewpoint. So that allows, then we render this point cloud of features onto a 2D image using a differentiable point cloud renderer that works sort of similar to the differentiable mesh renderer that we just saw. And this gives us now a feature map of our rendered point cloud that's been rendered from the new viewpoint. Then we can pass this to another neural network that then takes that rendered feature map and outputs an RGB image. And then the loss to train this thing has no 3D supervision whatsoever. The only supervision that we have during training time is pairs of images and their relative transforms in 3D space. So the supervision here is just that the predicted image should match the predicted image should match the ground truth image. And this thing is trained on just image pairs with no 3D supervision whatsoever. And because we're generating images, of course, we got to use a GAN, so we also train a discriminator on this thing jointly as well. And now the results are actually, I think, pretty exciting. So then we can actually take these single RGB frames at test time, and then predict these viewpoint change videos that allow us to render that viewpoint from novel viewpoints using only a single RGB image and using no 3D information in training.
The image on the top right and maybe even the bottom right, they kind of just seem like they're warping the image and not actually like generating a new angle. But like, are my eyes misleading me? I think because you're so used to seeing objects move in space that you don't appreciate like how difficult this is actually to do, right? Because you're right that you're warping the image. But in order to warp the image, you need to know what is the relative depths of all the objects in the scene, so that you know how different objects sort of transform differently in depth. So then on the left, you kind of need to know that these pixels at the bottom are actually closer to the camera, and the pixels in the back are farther away from the camera. And now in the right, you kind of need to realize that this is actually an occlusion boundary at the door, and then that there's actually a sharp discontinuity in depth.
So it's sort of learned though to predict these very high quality depth maps using no 3D supervision at all during training time, using only this 2D supervision information. I think also it's actually doing in-painting as well.
Yeah.
So because when you perform these view transforms, there will actually be pixels that come into view that are either coming off the edge of the image or coming off of disocclusion boundaries. So this thing is also doing in-painting inside the model to kind of cover up or invent new pixels around boundaries or disocclusion regions. But the fact that it just looks like it's warping the image means that it did such a good job with those in-painting that you can't even tell where it put in new pixels. So I think that that's actually a good reaction. But this is maybe our first big result in this direction of using differentiable rendering to do tasks to do 3D tasks without any 3D ground truth whatsoever. And I think pushing this forward in future, I'd like to explore maybe predicting not just novel view synthesis, but also full 3D shapes using similar types of techniques. So that gives us these 3 different tasks that sort of move beyond 2D recognition and kind of push towards higher level reasoning in sort of very different domains than these very basic recognition tasks. So I think we sort of had questions throughout, but if there's any more questions here, I'm happy to take them.
Yeah. So back in generating the 3D meshes, you are trying to generate parts of the object that you don't see. What if you try to just generate parts of the mesh that you could see? Do you think that might help any? Because it feels like you're asking a lot of the network to render parts of the object you haven't seen yet.
Yeah. I don't know, you can try it. But so I think that's, that's actually something I'd like to try going forward. And in particular, I think that allows us to scale up to new types of data sets. Because there's sort of these 3D scan data sets where people go around and kind of use 3D scanners to scan the 3D shapes of objects in the room. But for those data sets, you don't always get like the occluded surfaces of objects. So for example, there's these 3D scan data sets, but they don't always include like the undersides of tables or like parts under objects. So if you're going to scale up these sort of mesh prediction to those type of regimes, then you need to be able to deal with like only predicting the visible parts of objects.
So I think this comes to the second part of the talk, which is the physical reasoning. I was wondering if the spatial reasoning that you did in the first part of the talk, like in your PhD, would be useful to scale this physical reasoning tasks that you're trying to solve. Or do you think that they're completely?
I think they're kind of different. So a lot of the linguistic reasoning is really about language. And we actually don't use any language in the PHYRE benchmark. So the goals, we kind of wrote them out in natural language for like human consumption. So the goals here are something like maybe make the blue ball and the green ball touch. But in fact, these goals are not presented to the system in natural language. It's always the blue and the green object that need to be touching. So it's just sort of the color of the object is encoding the goal.
Right, so basically, I feel like it's so much effort put in to generate this particular template, so maybe the linguistic reasoning would help to generate more of these sort of data, maybe into 3D simulations or 3D goals and stuff. So
yeah, maybe. But I think any mechanism to scale the generation of these templates would be good, because we spent a lot of time manually designing these tasks, which is kind of fun, but takes a lot of effort.
Can you name a few applications of your last part of the talk? Like, I can see, for example, frame rate upsampling, but I guess that's the most obvious thing that I can think of. Probably is something else I have in mind.
Well, so for view synthesis, this is like the super standard, this is like a super awesome computational photography type of application. So for example, if you want to get 3D from a single image and kind of animate single images as a cool artistic effect. So that's something that people use novel view synthesis for. It also sort of lets you view existing RGB images in 3D. So suppose you wanted to like upload, like take a picture with whatever random picture that you want, and now maybe view it in AR or VR glasses. then you would need to generate binocular pairs that sort of looks at the scene from two different viewpoints. So it kind of lets you lift whatever random single RGB image that you have to be either view or manipulated in 3D.
Does it also help to use the last part of your talk where the view synthesis can be used for generating better, finer mesh models in the just previous work that you mentioned?
Yeah, I think so. Okay. Right, because they kind of occurred in the opposite order, which is why we didn't do it that way. But like any kind of 3D shape prediction is going to be better if you have sort of multiple views of the scene. So maybe you could sort of hallucinate alternative views, and maybe that helps you get better 3D structure. But then it's kind of a chicken and the egg problem, because if you were able to generate the good view from the other scene, that means you kind of already were able to predict the 3D structure pretty accurately from the single image.
This particular animation reminds me about a lot of games. So have you thought about any way of leveraging the game community to maybe like get better training data or like synthesize new puzzles for this?
So there, you take a good idea and you run into legal challenges. So it's true, there's a lot of games out there, but you can't just like take stuff that other commercial enterprises did and like repurpose it for your own goals. So there's some legal restrictions here, not technical restrictions.
Okay. But you could design a game that uses this and...
But that's kind of what we did, right?
Yeah.
Right. If you can't, you can imagine this is kind of similar to games that you might have played, but we kind of need to make it ourselves to make it all on the up and up. Yeah.
Do you see the 3D prediction in the Mesh RC event is it able to generate decent predictions if there's very good 2D predictions on those classes, but perhaps less supervised 3D data? And perhaps could you use like if you have some classification, you could use that as a prior in your for your 3D shape which you're refining?
Yeah, so I don't know, but that's not something we've looked at yet. But I think that's something I would like to do in the future, right? Because I think it would be useful if we could work in this like weakly supervised regime, where you could get like a lot of 2D annotation, but only a little bit of 3D annotation. So I think that's an important direction, but we just don't have any results on that yet. And the categories that we care to recognize are just like IKEA furniture, because that's the only thing that we can get aligned 3D data for. Yeah.
Talking a little bit about the part that you say that we don't need to rely on 3D supervision. So instead of using annotated 3D data set, what LLMs we can use to serve as a training data set for the model?
Yeah. So this is kind of a beautiful thing about deep learning. You don't actually need supervised data. You just need a way to get gradients, and you can get gradients using if you're clever, you can find ways to get gradients that don't require you to know the exact thing that you're trying to predict. So the slide is this one, right? So here you can imagine the pipeline is that our model is going to take the input image and then predict some kind of 3D structure. And then you can take that predicted 3D structure and render it back to 2D using your differentiable renderer. And now you've got like a rendered 2D image, which is like a rendered view of your predicted 3D shape. Then you can take your rendered view and compare it with the original image. And then that's just comparing like the 2D appearance of the rendered view with the original image that you had as input. So now the signal here is that you can then define a loss function that uses only 2D supervision on top of the rendered view of your predicted 3D shape. And if you can backpropagate through that renderer, then you can train the model that predicted the 3D thing, even if you did not have any supervision for what the 3D thing is that it should have predicted.
Do we need different perspective of that original input image?
Maybe, right? So this is actually a good point. So that's actually why we use, I think in this task of view synthesis, we rely on a discriminator to solve this problem. Right, so in view synthesis, right, the pipeline is that we predict a 3D structure, which is a point cloud of features. Then we render that point cloud of features from a new viewpoint. And then we use the rendered features to generate an image. But now the discriminator forces that the generated image has to look realistic. Because now the problem is that there's parts of the input image that won't have been visible once you change the viewpoint. right? Because like if you kind of move your head, then there's going to be parts that are going to come into view that were previously blocked by other objects, or the outside of the scene. So then to actually handle those parts, you need to rely on something, on some other thing. Whether it's maybe multi-view inputs is one idea, or in this project we use a discriminator to force the generated image to look realistic, even in this case where there were new pixels that had to be invented.
Okay, thank you very much. So with that, figure you like the whole pipeline where you are using differentiable renderer. If you have some annotated meshes by say humans or something, like maybe we can think about it as modeling say a latent space of couches, and then we can maybe come up with some LO-like objective, and I don't know how hard would that be to optimize.
Yeah, so there have been some approaches that do that kind of a thing, but I haven't seen it like really scale up to real world data to the extent that I'd like. So I don't really know if that's like a modeling problem or a data problem or like it didn't train for long enough and big enough models type of problem.
Right.
Because then we could like I've seen some projects where like you have a big collection of 3D shapes but they aren't aligned to images. Then you kind of like train a VAE type thing to learn some like LO-like latent space, and then you train a different thing that kind of predicts in that latent space. And then like that kind of like learned latent space then kind of takes the role of the discriminator in something like this.
Right. So the differentiable renderer can serve as like a generative model coming from the latent space back to the input space.
Yeah.
Yeah. Okay.
All right. And if there's no more questions, then thanks for having me.